So, we will discuss in this session about the solid catalyzed reaction. So, you see what we know generally about catalyst. So, those information first let us have a recapitulation, right, with some introduction of new points, and after that we will go for quantitative analysis in a simple geometry. So, first you see the catalyst, its synthesis and identification is entirely made by trial and error. Nowadays, there are certain simulation based on this density functional theory, then molecular dynamic simulations, etc., which somehow gives you the idea that okay, this will function as, this compound may function as catalyst, right. But experimentally, that is to be foolproof in order to justify your hypothesis. So, in general, what we have to note is that the selection of catalyst to promote a reaction is not well understood. Therefore, in practice, extensive trial and error is needed to produce a satisfactory catalyst. So, the selection of catalyst is based on, is finally based on repeated experimental trials. Number 2, say you know this iron catalyst, its function in the conversion of nitrogen and hydrogen into ammonia. But that does not mean that any form of this iron, if we use, right, it will be functioning as a catalyst. So, its process of synthesis, its crystal structure, everything, all components are important, not only the chemical composition, right. Its process of synthesis is particularly important. If you finally synthesize a catalyst material, knowing its composition only, it may not function as a catalyst at all, right. So, what is that? Duplication of chemical composition of a good catalyst is no guarantee that the solid produced will have catalytic activity. The observation suggests that it is the physical or crystalline structure which somehow impart catalytic activity to a material. So, catalysis depends on, or catalytic activity depends on chemical composition as well as crystalline or crystal, that is physical structure, as well as on crystal structure. So, duplication of any good catalyst does not guarantee the same catalytic activity, right. So, that is the second salient feature. Now, what will be the actual activity or actual functioning of a catalyst in relation to a reactant? So, the hypothesis is that somehow close to the catalyst, the reactant molecules are energized, right. they are somehow energized by the interaction, initial physical interaction or physicochemical interaction with the catalyst. They form a kind of transition complex, and in that transition complex the molecule, the reactant molecules are somehow energized, and which facilitates the reaction. So, it is thought the reactant molecules are somehow charged, energized or affected to form intermediate in the region close to catalytic surface. Various theories are proposed to explain the detail of action. We are not going into the theories. Right. The hypothesis reactant molecules are energized when close to the catalyst surface, and they form an active complex with the catalyst or binding with the catalyst. Right. Now, the most accepted form of the theory which explains the principle of catalysis is the transition state theory. Right. So, transition state theory catalyst, they proposes the hypothesis that catalyst reduces the activation energy barrier of or between reactant and product, reactants and products, without altering the equilibrium condition. Now, equilibrium, you see, it is a thermodynamic condition. The initial and final state remain unchanged, but intermediately it reduces the activation energy value. So, we can pictorially represent it. This the progress coordinate or progress of the reaction we are plotting here, and the y axis we plot energy. So, this is the reactant, this is of course the product at a lower energy state, and without catalysis it is something like this, with catalysis it is something like this. So, without catalyst, and this is with catalyst. Right. So, pathways of the reactions are different, and you see that this is the activation energy barrier with catalyst, and this is the activation energy barrier without catalyst. Right. So, this is always higher than activation energy barrier with the catalyst, and as a consequence we have a favored effect which we call the catalysis. Right. Now, since we have already mentioned that it is not altering the equilibrium. So, next is, since the surface is responsible for catalytic activity, a large rapidly accessible surface is easily handled material is desirable. By a variety of method, active surface area of the size of football field can be obtained per unit cubic centimeter of a catalyst. So, it must have a porous structure, right. A catalyst must be highly porous and must allow the diffusion of reactants to the active sites to its active sites. Right. So, it must have a very high area, internal area, right. So, it must be naturally porous. So, from here we have to note what are the steps in the process of diffusion, process of catalytic reaction. So, you see why it is important that we have a mass transfer aspect. So, from this external bulk of the catalyst, the reactants are diffusing into the catalyst and it is moving towards the active sites, then it is getting adsorbed, then surface reaction takes place, products are formed in the adsorbed state, then it may be desorbed and there will be counter diffusion. So, there are several steps involved in a catalysis. So, let me jot down the steps. Number 1, diffusion of reactant through the external film over the catalyst. Like if you have the catalyst particle like this, there will be an external film and you have the bulk gas or bulk liquid flowing like this. So, from here this pathway that through the film the reactants are diffusing from the bulk to the external surface of the catalyst is the first step. Pore diffusion of the reactants. Adsorption of the reactants onto the active sites of the catalyst. Surface reaction between adsorbed reactants. Desorption of the products. Counter pore diffusion of the products and counter diffusion of the product through the external film. Right. So, here you see, if we explain it with the help of a diagram, it is better here to understand the different steps. Let us consider this is the catalyst particle, and here we have a single pore which may be having branches, etc., etc. Right. And there are active sites over here on the surface of these pores. And we have an external film. Now what happens? Here we have a concentration Ca0. So it diffuses here. Definitely there must be a concentration gradient. So this is process 1. Next, it diffuses through the pores. Next, it's adsorbed onto the pore. Right, process 3. Next, the surface reaction takes place, process 4. Next is desorbed, counter diffusion. Desorption is step 5, counter diffusion, pore diffusion is step 6, and counter bulk diffusion is step 7. Right. So try to note that first we have the diffusion of the reactant through the external bulk or external film. Next, it is the diffusion through the pore and reaching the active sites here. Next, it is the adsorption. Next, it is surface reaction. Next, it is desorption of the product, counter pore diffusion of the product, and counter bulk diffusion through the external film. Right. So these are the steps. For this time being, we will focus on these two steps. Right. So whether it is, so from this point, we will try to ask the question whether it is pore diffusion controlled or surface reaction controlled. Now the competition between adsorption, surface reaction and desorption we will discuss later in supplementary material and supplementary lectures, right. So there we will see that what is referred as the single side, dual side mechanism, what is Ehlers-Danlos mechanism, etc. But for this time being, we will focus on these two steps. Whether the pore diffusion controlled means whether this pore diffusion is the slowest step, it is the most time taking step, and that determines the time of catalysis, or it is the reaction which determines the time of catalysis. So controlling, rate controlling steps means the slowest step in the overall process, right, and the time required to execute that step is basically same as that of the time required to execute the overall process, because this either this or this will be the most sluggish process, and relative to the time scale of either of this or either of this, whichever is the rate controlling, all the others we are considering right now are instantaneous, right. So with that understanding, let us move to condition or fetching out the condition which will determine that whether it is pore diffusion controlled or reaction controlled, right. And for this purpose we consider a simple geometry of a single cylindrical pore. So we will consider the pore diffusion resistance combined with surface kinetics. Pore diffusion resistance combined with surface kinetics, a single cylindrical pore and a first order reaction. Now, we consider this is the external wall of the catalyst. We consider a single straight cylindrical pore having a dead end. Now, you see that actually the pores are tortuous. So, that is accounted by tortuosity and all. This is a different formalism, but we simply curtail that and we simplify this into a single cylindrical pore, right. And generally what happens, the pore radius is R and the length of the pore is L, right. Generally what happens, R is much smaller than length. So, we consider only axial variation of the reactant, where Z is from here, Z equal to 0 here and Z equal to L here. So, these are the solid walls where we have the active sites. Right. So, here to generate the concentration profile, we will consider this sort of differential control volume. Between Z and Z plus delta Z. So, if you look into this and enlarge the view with different influxes. So, what we will see? This is R. Here we have the diffusive flux. So, minus d del Ca del Z at Z. And here moving out is minus d del Ca del Z at Z plus delta Z. We can multiply it by pi r square, here also by pi r square. Now, on this surface, this curved surface, we have the reaction. The kinetics is minus Ra prime is equal to K prime Ca or minus Ra is equal to Kca. The basis here is the volume of the reactant. Sorry, here the weight is of the catalyst, as it is prime sign we have used, and here it is the volume of the reactant. And the reaction A giving product is going on. Right. So, we will write a steady state balance over this differential shell or the control volume. Steady state balance over the differential shell. Steady state balance of reactant. Right. So, inflow is minus of d dCA dCA dZ at Z into pi r square, outflow right, inflow minus outflow minus accumulation by chemical reaction. So, we can also use minus Ra double prime, which is based on the catalyst surface area. So, let us use minus R A double prime. So, minus of minus R A double prime, right, into this pi r square delta z. Oh, sorry, not pi r square, it is 2 pi r area into delta z, that is equal to 0. So, this must be is equal to k double prime into C A. So, what we will have is this divided by delta z, and so we have dE into dCA dz, d square Ca dz square minus k double prime into Ca into 2 pi r divided by pi r square equal to 0. So, we have dE d square Ca dz square minus 2 k double prime divided by r into Ca equal to 0. Now, you see this minus of Ra double prime is equal to minus of 1 by S dNA dt equal to k double prime into Ca, whereas minus of Ra is 1 by V based on the volume of the reactant dNA dt equal to kCa. So, we can just write S into minus of Ra double prime is equal to V into minus of Ra. So, which means the surface area is 2 pi r into delta z into k double prime into Ca is pi r square into delta z, volume of the reactant, that is same as that of the volume of the pore over this differential shell, into k into Ca. So, this Ca cancels out, delta z cancels out, pi cancels out. So, k is equal to 2 k double prime divided by r. So, we have equation 1, we have equation 2. So, let us combine these two. So, combining equation 1 with 2, we have d square Ca dz square minus k divided by dE into Ca is equal to 0, and that we write as d square Ca dz square is equal to or minus m square into Ca equal to 0, where m is equal to under root of k by dE. Right. So, here this is to be solved, and my boundary condition z equal to 0, Ca equal to Cas. At the pore mouth, what is the concentration? Here, Ca equal to Cas. And at z equal to L, it's a dead end, so there will be no further diffusion. So, dCA dz equal to 0. So, this equation along with the boundary condition we have to solve. This is a very simple boundary value problem, and we know the solution will be C1 into e to the power mx plus C2 into e to the power minus mx. Right. So, the solution is, let me erase this part. The solution is Ca equal to C1 e to the power mz plus C2 e to the power minus mz. So, you see z equal to 0, Ca equal to Cas is equal to C1 plus C2, and dCA dz is C1 m e to the power mz minus C2 m e to the power minus mz. So, dCA dz at z equal to L, which is C1 m e to the power ml minus C2 m e to the power minus ml, that is 0. So, C1 by C2 equal to e to the power minus ml by e to the power ml. Right. So, if I substitute it, CAS is C2 into e to the power minus ml by e to the power ml plus C2. So, C2 is e to the power ml divided by e to the power ml plus e to the power minus ml, and C1 is of course e to the power minus ml divided by e to the power ml plus e to the power minus ml. So, if I substitute it in this equation, we will get what we will get, that Ca is equal to C1 e to the power minus ml into e to the power mz plus e to the power ml, C2 is e to the power ml, e to the power minus mz divided by e to the power ml plus e to the power minus ml into CAS. Definitely there will be CAS, I think, yeah, there will be CAS. So, this is e to the power m L minus z plus e to the power minus m L minus z divided by e to the power ml plus e to the power minus ml, and that is CAZ by CAS, and which we can write easily as cos hyperbolic m L minus z divided by cos hyperbolic ml. So, that is the concentration profile. So, based on the value of Ca by CAS, this is 1. So, based on the concentration profile, based on the values of m and L, right, Ca by Cas will change. Like here, if we plot Z by L, this is 1, this is 0. So, the values will be like this. So, just like ml is 0.5, 1, 2, 3, and here ml is 10. Right. So, this dimensionless quantity ml, what is that? Under root of k divided by dE into L. Now, this is a first order reaction. So, this is 1 by second meter square per second into meter. So, it is dimensionless. And that ml we refer as Thiele modulus. For here the for first order reaction, irreversible reaction. Definitely the Thiele modulus will change as you go on changing the type of the reaction from first order irreversible to first order reversible to first order nth order irreversible, etc. So, now we have to think that what is the role of, or quantify what is the role or how much dominating is the pore diffusion. So, we introduce effectiveness factor epsilon as let me check the name, yeah, effectiveness factor. So, this is simply actual reaction rate within the pores divided by reaction rate without pore diffusion. Just try to understand that concentration decreases, right, along the pores. So, this value epsilon, the effectiveness factor, will be close to 1 if the system is reaction controlled. Why? Because if it is reaction controlled everywhere and diffusion has got negligible role to play, everywhere inside the pore the concentration will be CAS. Whereas, if I have a pore diffusion is dominant, and which we see it is increasing with the increase of this Thiele modulus. So, what will happen? The value, the concentration rapidly drops within the pores. So, this we can write as this K into Ca average, right. So, it is average concentration inside the pore, right, divided by K into CAS. So, average means 0 to L CAZ dz and denominator is CAS into 1 by L. So, 1 by L 0 to L CAZ by CAS dz. So, see, already we have solved for the concentration profile. Let me now erase this part. We have solved for this concentration profile. So, effectiveness factor is 1 by L 0 to L cos hyperbolic m L minus z divided by cos hyperbolic ml dz. Because Ca by Cas we have solved to be just like the expression, right. So, you see this integral will give you cos hyperbolic m L minus x into d of L minus z d of L minus z. There will be an m, there is a minus sign, by cos hyperbolic ml integral 0 to L. So, this will be, see, integration e to the power x minus e to the power minus x by 2 dx equal to e to the power x minus of e to the power minus x by 2. So, it will be sine, right. Cos hyperbolic integration will be sine. So, minus of 1 by ml sine hyperbolic m L minus z limit 0 to L divided by cos hyperbolic ml. Now, when it is L, sine hyperbolic 0 is 0, and when it is 0, this is sine hyperbolic ml. So, there is a negative sign because of the lower limit, and that negative cancels out with this. So, finally, sine hyperbolic by cos hyperbolic gives you tan hyperbolic ml by ml. So, that is epsilon. And alternatively, we can use a different symbol, that tan hyperbolic Thiele modulus by mt, right. So, what happens if the Thiele modulus is less than 0.4, epsilon is close to 1, and when MT is greater than 4, epsilon can be fairly approximated as 1 by MT. So, the nature of the graph MT and epsilon in double logarithmic space is something like this. This is the asymptote for low value of MT and this is the asymptote for high value of MT. So, this asymptote is epsilon equal to 1 by MT, this asymptote's equation is epsilon equal to 1. So, actual curve is something like this. Right. So, here we have MT equal to 0.4 and close to here this is MT equal to 4. So, in this region where epsilon value decreases, right, much below 1, this is value 1, much below 1, then we can say it is a pore diffusion controlled regime. So, this is pore diffusion controlled regime in this direction, right. This is the reaction controlled regime and this part is the intermediate regime where both the pore diffusion or neither the pore diffusion nor the reaction is a rate controlling state, both governs the reaction. So, here we will go for some understanding in relation to this. So, first it is the diffusion coefficient. So, first we have to use effective diffusion coefficient, that is dE. Why? Because the catalyst pores are of very small radius such that Knudsen diffusion may be important, may be dominant or may be important in addition to molecular diffusion. Right? So, 1 by dE is equal to approximately, this is not the exact formula, 1 by dm plus 1 by dk. We have discussed it in mass transfer. So, this is the molecular diffusivity, this is the Knudsen diffusivity. Right. So, that we have to consider. Next, measure of pore length L. You see, L is equal to for irregular particle it's equal to volume divided by external surface area, right. For rectangular parallelepiped we have L equal to thickness by 2. Like if you have the catalyst particles in the form of rectangular bricks, right. So, it is the thickness by 2, and it is equal to R by 2 for cylindrical particle and equal to R by 3, radius by 3 for spherical particles, spherical catalyst pellets. So, this is for cylindrical, this is for spherical, right. So, that is the pore length estimate we should have. For irregular shaped, it is the volume divided by the external surface area. For the rectangular block, it is the thickness by 2. For cylinder, it is R by 2, and for sphere, it is R by 3. Now, we have rate expressions or rate equations. What we are going to use? We can use this minus Ra, the basic one what we have defined, 1 by V dNA dt, where V is the volume of the reactant. We can use minus Ra prime as minus of 1 by S dNA dt, sorry, minus of 1 by W dNA dt, where W is the weight of the catalyst. We may use minus Ra double prime is equal to minus of 1 by S dNA dt, where S is the surface area. Additionally, here we are introducing R3 prime as minus of 1 by Vp dNA dt, where Vp is the volume of the catalyst pellet. Right, and finally minus Ra 4 prime equal to minus of 1 by Vr dNA dt, where Vr is the volume of the reactor. So, these are the specification of rate equations, and you see in the handout we have I have mentioned that A giving R in a manner similar to what we have done for a single cylindrical pore, Thiele and Aries related epsilon and empty for various catalyst pellets, right. So, their derivations it is given in the book of Fogler. So, we are not going for the derivation. So, here it is minus Ra triple prime what we are using, and that for first order, let us say. So, it is effective rate is epsilon into K triple prime into Cas, right. K triple prime into Cas, where Cas is the concentration at the pore mouth. In the handout, it is wrongly stated initially in the equation 23 and 24, right. In relation to that, there is a typo, it is written as 4 prime, but actually it is 3 prime, right. So, for these cases, so epsilon is equal to what? It is equal to tan hyperbolic by mt, the same expression for rectangular parallelepiped shaped catalyst pellet. It is equal to I1, the Bessel function of the second kind, 2mt by I0, 2mt. You do not have to remember it. for cylindrical pellet, and it's equal to 1 by mt, and there will be 1 by mt obviously, 1 by mt, 1 divided by tan hyperbolic 3mt minus 1 divided by 3mt for spherical pellets. Okay. So, first is the regarding diffusivity, second is in relation to the length L, third in relation to the rate expression, and again for the considering the first order process, these expressions of epsilon, they are derived, there is a complicated algebra, we are not going into that, right. But why we are not taking considerations of the different expressions? There is a reason. The reason is, for whatever it is, it may be cylindrical, it may be rectangular pellet, it may be spherical, the epsilon versus mt profiles are nearly same as that of, this is a log plot, right. This is 1, here we are plotting epsilon, and this is mt. This is of slope 1 minus 1, because epsilon equal to 1 by mt here. So, epsilon equal to 1 by mt or nearly equal to 1 by mt. So, log of epsilon equal to minus of log of mt. So, this is log profile must be a curve of slope minus 1. So, close to 0.4, see what are the nature of the curve. These are the natures for different types of shapes, right. Like this one for block, the second one for the cylinder, the third one for the sphere, right. And this is 4, this is nearly 0.4. So, the nature of the plot for this rectangular parallelepiped is practically remaining same. So, 4 we have pore, this topic is pore resistance limits. For all different shapes of catalyst pellets, in case of first order reaction, if mt is less than 0.4, it is reaction controlled. That is, epsilon is close to 1. If mt is greater than 4, then it is pore diffusion controlled. Epsilon is close to inverse of mt, right. So, that is the inference 4 we have. Now, inference 5. Now, when it is strong pore diffusion controlled, when it is, or here actually we can write that C for mt less than 0.4 minus Ra1 divided by minus Ra2 epsilon 1 kCs by epsilon 2 kCs epsilon 1 by epsilon 2 close to 1, and 1 and 2 are values for two different particle size or pellet size. However, for mt greater than 4, minus Ra1 by minus Ra2 is equal to epsilon 1 by epsilon 2 1 by Mt2 by Mt1. Now Mt is proportional with the size, so we can write pellet size 1 by pellet size 2. Why? Because Mt is proportional to L and L is equal to R by 2 or R by 3 for cylindrical, the commonly available cylindrical or spherical pellets. So that's the fourth point we have to note and remember. Right. There are some extensions as well. Extensions of features. So primarily we have discussed 4 major points in relation to the straight cylindrical pore problem, where we have derived this epsilon equal to tan hyperbolic Mt by Mt, and we have discussed about the different controlling regimes like diffusion controlling or pore this reaction controlling. Additionally, we have discussed about the thickness, this L, which is thickness by 2 or R by 2 or R by 3 for different geometries. Now for first order reaction taking place over a cylindrical pellet or the spherical pellets, there also we have derived the expressions of epsilon, and finally we have discussed about the different controlling regimes for the different values of telemodulus. Next, for arbitrary reaction kinetics, Mt is equal to minus of R triple prime at Ca is equal to Cas divided by under root. This can be proved, but I am not going for the proof. Cae to Cas minus Ra triple prime dCa into L, I think, yes. Right, where Cae is the equilibrium concentration. And minus of Ra prime, Ra triple prime is based on the pellet volume. Right? For first order reversible reaction, Mt equal to L under root of K triple prime divided by D into Xae, and Xae is the equilibrium conversion. Right? Now for nth order irreversible reaction, Mt equal to L under root of K double prime, K triple prime, n plus 1, Cas to the power 1 minus n, right? Sorry, Cas to the power n minus 1 divided by 2d. And this gives you a very, very important consequence, right? So let the nth order irreversible reaction operates in pore diffusion controlling regime. So, see what happens. This is taking place in pore diffusion controlling regime. Right. So, epsilon equal to 1 by mt and minus Ra triple prime effective is equal to epsilon into k triple prime into Ca. So, epsilon is 1 by mt. So, that is equal to 1 by mt into k triple prime into Ca. Ca to the power n, sorry, Ca to the power n, because it is nth order reaction. So, it is L or it is 2dE divided by k triple prime into n plus 1 Cs to the power n minus 1, this is Cs, into L, right, into Cs, this is Cs also, to the power n. So, there is a peculiar thing what is happening. We will have in the effective reaction, we will have a different order from that of actual nth order. So, that is the apparent order of the reaction what we observe if a reaction operates in strong pore diffusion regime for an nth order irreversible reaction. So, what will be the order here? Yeah, and here definitely there is k triple prime, right. So, L, let us finally summarize, 2dE divided by n plus 1, right, n plus 1 into k triple prime to the power half into Cs n minus 1 n minus 1 by 2, which is n plus 1 by 2. So, to the power n plus 1 by 2. So, this is the apparent order of a reaction, right. And additionally, this we can write L 2d divided by n plus 1 into k triple prime 0 into e to the power minus E activation by RT into 2. So, Cs to the power n plus 1 by 2. So, apparent activation energy is original energy by 2 and apparent order is equal to n plus 1 by 2. So, that is the peculiar observations what we have in case of nth order irreversible reaction taking place in strong pore diffusion regime. So, lastly we will discuss about the different fundamental equation of reactors containing porous catalyst pellets. Equation for reactors with porous catalyst pellets. So, basically we can go by this input minus output and all, right. So, we can have this for this plug flow reactor PFR. So, the equation, performance equation will be W divided by Fa naught equal to 0 to Xf, just like the normal plug flow minus Ra prime, or we can have Vp divided by Fa naught is equal to 0 to Xaf into dxa divided by minus Ra triple prime, right. So, you see that here tau prime is equal to Ca naught into W divided by Fa naught and here tau double prime is equal to Ca naught into Vp by Fa naught. And they are referred as the wet time and volume time. So, this is not the space time, this is referred as wet time. Why? Because our basis has been changed from the volume of the reactant to the weight of the catalyst, and here from the volume of the reactant to the volume of the pellets. So, that is why this is called the volume time. So, whatever may be the reaction, we can substitute here and we can integrate and get the respective design equation. Now, for mixed flow reactor, similarly we have W divided by Fa naught equal to tau prime divided by Ca naught equal to XAF minus XA0 divided by minus Ra prime, or alternatively Vp divided by Fa naught is equal to tau double prime divided by Ca naught is equal to XAF minus XA0 divided by minus Ra triple prime. Just like very similar to the normal plug flow reactor and mixed flow reactor. Now, lastly we will try to discuss the experimental method of finding the rates. So, again you see there are two different methods, one is the integral approach, another is the differential approach, right. But batch reactor we can also use. So, what are the different types of reactors? First, experimental reactors that we have to understand. First one is a batch, second one is MFR, third one is PFR, and fourth one is differential reactor. Right. Now, for batch, we can write the equation very similar to the plug flow reactor basically. Okay. Now, question is, what is the differential reactor? This is a new issue. If the conversion or rather the change of conversion from inlet to outlet of a reactor is very small, we may write, what we can write that, we can write for PFR basically, W by Fa naught equal to XAF minus XA0, here we can have XA0 as well, then minus Ra prime at XA average, right, or Vp divided by Fa0 is equal to XAF minus XA0 divided by minus Ra triple prime average. So, that is the idea of differential reactor. We have a differential flow reactor when we choose to consider the rate to be constant at all points within the reactor. Since the rate are concentration dependent, this assumption is usually reasonable only for small conversion, right, or a shallow small reactor. So, this is the idea of a differential reactor. Integral reactor or integral analysis, you see this differential reactor we have discussed. So, next is the integral analysis or types of analysis. What you can do? We can go for integral or differential, right. In integral analysis, we will use the PFR formula that W by Fa naught is equal to say XA naught to XAF dXA by minus Ra prime, or Vp divided by Fa naught is equal to XAI to XAF dXA by minus Ra triple prime. So, we will consider, so here we have to go for assuming a rate expression just like batch. right, and integrate it, convert it to the linear form and check whether the linear form is satisfied with this reactor data upon changing W, upon changing this flow rate, etc. Now, differential reactor is something, see, if you take the derivative of this formula, we will get that d of W by Fa naught is equal to dxa by minus Ra prime. So, we have dxa d of W by Fa naught is equal to minus Ra prime. So, what we can do? We will plot this W by Fa naught. Say whatever it is. Now, here the derivative at each and every point will give you the respective rate, and at that point, as if xa is known, we can solve for the concentration and generate this minus Ra prime versus Ca plot. So, differential analysis we have done, mixed flow reactors we have discussed, and there are, though I am not discussing it, it is given, the diagrams are given in the handout, that there are two types of experimental mixed flow reactor. One is called the spinning basket reactor, another is vortice reactor, and there is also a configuration given in the handout for the batch flow reactor. So, that is all for this initial discussion of solid catalysis, right. So, in these supplementary sections or in these additional sections, whatever I have missed from different subjects, we will discuss about this single side, dual side mechanism, LEDL mechanism, the remaining part of this catalysis. So, in the next session, we are going to move to non-isothermal reactor design and finally the RTD. The two chapters, these two are still to be completed, right, for the baseline completion, but for the baseline syllabus. And next, once we cover the other these subjects like mechanical operation, project engineering, then we will discuss about the remaining parts of the different subjects, just like the epsilon NTU method, we have a leftover in heat transfer, then this reaction engineering, then some part of the control valve, etc. Thank you.